Just as the Harry Carey skit from SNL states, space truly is an infinite frontier. Questions about space seem to pop up daily due to its mysterious nature, and black holes are definitely no exception to that. They're such a fascinating phenomenon that many people have misconceptions about, so that's what we'll be talking about. It's black holes in plain English. So we'll begin with how a black hole is formed, and later we'll talk about what it actually is. So the birth of a black hole begins with a massive star, 10 to 25 times the size of our sun, which is represented by this tiny pixel down here, and these are size comparisons of other known stars in the universe. So stars live by using lightweight elements present on the star, such as hydrogen, to combine with each other to create heavier elements such as helium. And this is done in a process called nuclear fusion, as you can see here. We have a hydrogen atom and another hydrogen atom fusing together, forming this helium atom. And this continues on until the star uses all the elements present, and there's nothing left. So just like on Earth, there is a gravitational force on stars, and since the stars are much more massive, their gravity is going to be much more massive as well. Gravity is part of a push and pull system, or an action-reaction system, if you'd like to look at it that way. The core of the star exerts a force on the elements toward the surface of the star, and the elements at the surface exert a counteractive force on the core of the star. But once the elements are used up in the nuclear fusion process, the gravity of the core can only be exerted on itself. So it results in an explosion. And this is where the star essentially blows up on itself, resulting in what's called a supernova explosion, as you see here. So depending on the original size of the star, it's going to have a unique Schwarzschild radius, as I've drawn for you here. And you may have also heard of the Schwarzschild radius being referred to as the event horizon. Now, the radius here creates this area known as the event horizon, and basically what it is the radius designates the boundary at which the dying star will continue collapsing in on itself toward infinity. So gravity becomes the ultimate power, and nothing can escape its force. So if the star, original star, which we have here highlighted in orange, if it explodes in on itself within this radius, it will continue shrinking and collapsing in toward infinity, to where gravitation is at an infinite level. And so anything coming within the area is unable to escape, and that includes light, which travels at 3 million meters per second. So it's pretty fast. You can tell that these black holes are pretty powerful animals. If you want to look at the speed in a different with a different perspective, you can look at it as 671 million miles an hour, or 186 miles per second. So in any case, light is pretty fast, but the black hole's gravity is able to prevent it from moving an inch. So here's a little diagram of the process of the black hole's formation that we've covered so far. In the left side, you got a star just doing its thing and shining. And then if you move over to the right here, we have the star that's begun to collapse in on itself. The arrows represent light rays that are trying to escape from the surface of the star. But they can't escape in a straight line like a normal light ray would, because of the immense gravity exhibited by the collapsing star. Notice the photon sphere here that's shown in the dotted line. The sphere is simply an area that extends out past the Schwarzschild radius a little bit, and in this area no light is able to escape, as you can see from the arrows that have been turned completely around. So as we progress through this diagram, we can see that less and less light is able to escape. As you see here, those light ray arrows are sharply turned around, and so eventually it all closes up and it forms this black hole where all the gravity is pointed toward the center. So now we have a black hole running around on us, and this is what an artist's rendition of it might look like. Now that we have it running around, we need to understand what it's capable of doing. First, you want to recognize the singularity, which is the very, very center of the black hole there. Now, this isn't just a ball of stuff that the black hole has collected. It's nothing more than an empty space of infinite gravity and density. Anything that reaches a singularity is completely annihilated and removed from existence. But this goes against the universal law of conservation of mass, which tells us nothing can be created nor destroyed. Things aren't made from thin air, they're created from pre-existing materials. Take an ice cube, for example. Not that ice cube. Wrong ice cube. Here we go. Take an ice cube, for example. The solid ice isn't completely eliminated as matter at the singularity of a black hole is. It's simply melted into a different state of matter into liquid. So this is why black holes are so fascinating. They completely defy the scientific laws that we've held to be universal and apply to everything, but obviously they don't uphold these scientific and physical principles. Einstein himself developed mathematical equations that actually predicted the existence of black holes, but he refused to believe his own equations. So how do we know that the existence of black holes is accurate? I mean, they're in space and they're black, and space is black, so how can we see all this stuff going on? Well, one thing is that it can pass in front of bright objects behind it, and so up against this bright surface we can see this massive black blob, as you see here. Another observable feature that black holes exhibits is its tendency to display gravitational lensing. If you take a look at this will show you exactly what gravitational lensing does. So here on the left we have Earth, and on the far right are a group of galaxies or bright celestial objects. In the center is a massive object. In our case, it's a black hole. So as the light passes from the galaxies toward Earth, it has to travel past the black hole first. And what do we say about black holes doing to light? It can trap it. However, in this case, if the light is in a safe distance, it's only going to be bent a little bit around the black hole, just like a magnifying glass might do with light, displaying an inverted image. It distorts your image, and you can see how it might do that with a magnifying glass. When held at a certain distance, the light that penetrates the magnifying glass is inverted and distorted so that it appears upside down, as you can see here. So, despite the dreadful outcome of every possible encounter with a black hole, we needn't fear the black hole as long as we're living on Earth. We're safe enough distance from any black hole and any massive star that may turn to the dark side. So for now, why not just kick back, get yourself freshly poppable popcorn, courtesy of the Bio and Ag group from Section 1, and put in a quality presentation, feature presentation. There's Event Horizon, while you still can. Just kidding, you got plenty of time, so enjoy it.